Hello guys, and welcome back to the PyTorch tutorial series. In the previous video we discussed about the first kind of model known as linear regression. We have covered in detail about the theory and implementation of the linear regression model using PyTorch. In this video we're going to pick up from where we left off and discuss about the theory behind logistic regression. After the basics of regression, it is time for the basics of classification. And what can be easier than logistic regression? This is what classification actually means. It is as simple as dividing a waste. You can consider regression a different kind of task where we want to predict something which is continuous, and classification is sorting out the difference between a set of classes. So we have saved the easy algorithms for the last, and we'll continue on learning about logistic regression. First, let's start by defining the meaning of logistic regression. In the machine learning world, logistic regression is a kind of parametric classification model. Despite having the word regression in its name, many people make the mistake of considering logistic regression as a model that is used to solve regression problems, because the name also has regression with the task regression in its name, so they automatically consider it that it could be used to solve regression problems. But it's actually a classification model. It's a classification algorithm that is used where the response variable is categorical and not continuous. The idea of logistic regression is to find a relationship between features and a probability of particular outcome. So if you want to predict something which is categorical and you want to learn the relationships between features and the probability of a particular outcome, then you can select logistic regression to solve that problem. Next, let's see the types of logistic regression by considering an example. For example, when we have to predict if a student passes or fails in an exam when the number of hours spent studying is given as a feature, the response variable has two values, which is pass and fail. So whenever you consider a problem where you want to predict that a student has passed a certain class by considering their scores, so passing and failing is a categorical classification problem, so we can use logistic regression to solve that problem. This specific type of problem is referred to as a binomial logistic regression, where the response variable has two values, 0 and 1, or pass and fail, or true and false. So whenever you have two categories that you need to identify, then that type of logistic regression is called binomial. There is also another type of logistic regression known as multinomial, which deals with situations where the response variable can have 3 or more possible values. So when you have a multi-class classification problem, you have to use a multinomial logistic regression, which is also kind of the same thing as the multinomial case that we have covered in linear regression. So why logistic and not linear? With binary classification, let x be some feature and y be the output, which can be either 0 or 1. Then the probability that the output is 1 given its input can be represented as p, the probability of y equal to 1 given x. So given an input feature x, if you want to predict the probability that y could be either 0 or 1, can be represented using this method, and this is known as a conditional probability, where you predict one variable given that the other variable has already occurred. If we predict the probability via linear regression, we can state it as p of x is equals to py equal to 1 given x. Let's consider these two representations are the same. Then by using this formula, we can use p of x is equals to b naught plus beta naught plus beta 1x. So this representation is just replacing the probability of y equal to 1 given x. So if we want to answer the question why logistic and nonlinear, here we're using a linear equation in order to solve a classification problem. So if we want to use linear regression to solve this kind of problem, it can generate the predicted probability as any number ranging from negative to positive infinity, whereas probability of an outcome can only lie between 0 and 1. So if you have taken any kind of probability class, you might have learned about that one rule that must not be broken about probabilities is that the probability of a certain variable has to lie between 0 and 1, and linear regression breaks that rule because the output that you get from a linear equation can range from negative to positive infinity, because the domain and range for a linear regression equation ranges from negative to positive infinity. So let's consider this logistic regression problem where we have one set of outcomes equal to 1 and another set of outcomes equal to 0, and we represent them as dots, and we want to classify these two sets of classes by using a linear equation line. You can see that the line is not separating the classes very well. Also, linear regression has a considerable effect on outliers. To avoid this problem, the log odds function or logit function is used. That's why the name that's where the name logistic regression comes from, because of the fact that we're using a logit function in order to solve a classification problem. So next, let's talk about this logit function in detail. We can improvise the linear equations that we have seen previously, where the outcome was just p of x is equals to beta naught plus beta 1x. This can be expressed by using a logit function, and we can improvise it in this way, where the left hand side is called the logit or log odds function, and the division p of x by 1 minus p of x is called the odds. And what do we mean by the odds? The odds signify the ratio of probability of success to probability of failure. This is also one thing that you might learn from introduction to probability class, is that the odds is the ratio between the probability of success and the probability of failure. Therefore, in logistic regression, linear combination of inputs are mapped to the log odds, where the output is being equal to 1. And if we take an inverse of the above function, we get this equation. So if we take the inverse of this equation, we can consider that we have the p of x here, and we have e to the power of beta naught plus beta 1x divided by 1 plus e to the power of beta naught plus beta 1x, and this is the equation that we need for predicting the output from our input x. Once we get this equation from the logit function, we call this representation known as the sigmoid function. And you might not have seen this formula being used to represent the sigmoid function, but you might be familiar with this representation. But both representations are the same. We just need to divide it by e to the power of beta naught plus beta 1x here, and you'll get this representation. So this is known as a sigmoid function, and it gives us the S-shaped curve that we need in order to solve the previous problems that we mentioned here, where we want to classify these two set of classes. So an S curve could be a function that could be suitable to solve this kind of problem. Sigmoid function can be defined as follows, where Z denotes a classification line that resembles linear regression. This is Z is equal to W transpose X plus B, where it's simply a linear regression equation, and E is the natural logarithm base. The sigmoid function's output values get closer to 0 and closer to 1 as X moves toward positive and negative infinity. So as you can see from this S curve, you can see that when the values get closer to 0 or get closer to 1, X moves towards positive and negative infinity, respectively. And the observation is then classified as positive if the predicted probability exceeds a threshold, which is commonly set at 0.5 in order to determine the predicted class. So normally what we do during logistic regression is by setting a threshold value of 0.5. If the predicted output from our logistic regression model is greater than that threshold value, which is 0.5. Here in this case, the blue dot represents a y value of 0.8. Since this value is above the threshold, then the output can be predicted as 1. And if the predicted probability value is less than the threshold value, then it can be classified to the next set of class known as 0. However, there are several important properties that should be mentioned. Nonlinearity is the first property. When we talked about the linear regression algorithm, we have mentioned some assumptions that we must consider before implementing that type of model. We mentioned that linearity is one assumption that we must consider before selecting the linear regression model. But logistic regression is the opposite. Nonlinearity is its first property and not linearity. The relationship between the input and the output is not a straight line, since the sigmoid function is nonlinear. So the logistic function and the sigmoid function that we have seen before is an S-shaped curve, and it's not linear, as you can see, because the curve is S and not a line. So it is a non-linear function. Second, the output values of the sigmoid function follow a recognizable S shape, as may be seen on the image, with a positive infinity for x approaching 0 and a negative infinity of x approaching 1. The sigmoid function is differentiable. This is the second property, which implies that it has a derivative that can be utilized for optimization tasks like determining the function's maximum or minimum. So whenever we select a function for predicting the output, we must consider that it should be differentiable, because when we want to perform backpropagation, we want that function to be differentiable, otherwise it might complicate the rest of the training procedure. The next thing that we should cover is the binary cross-entropy loss function. The BCE loss is a common loss function in machine learning, especially for binary classification issues, and it calculates the difference between a binary target variable's true label and anticipated probability. And in binary classification, the objective is to predict the likelihood of the target variable given a set of features. We have already covered the different types of loss functions used in PyTorch in the videos that I made about loss function. So we have already discussed in detail about the representation of the binary cross-entropy loss function. So if you need more information, you can go and watch that video in order to understand how the loss function works in detail. But here we have a summary of the BCE loss, where the target variable can only take on two values, 0 and 1. So here Tn is a true label, which can be either 0 and 1. So this is a different representation that you might not be familiar with, but this representation shows that T is a true label and Y is a predicted probability from our model, and J is the objective function that we try to minimize or maximize. We have already mentioned that the sigmoid function is a differentiable function, so when we start the back propagation, we can start by computing the partial derivative of the cost function j with respect to the variable y. And this is a representation. We can also differentiate it with respect to the activation function a, and a can also be, we can also consider the partial derivative of a with respect to w. Then the partial derivative of the original cost function with respect to each weight can be the product of all of these partial derivative values that we have computed above, and by multiplying them using the chain rule, we can find the partial derivative of the cost function j with respect to the weight parameter. So the purpose of the backpropagation algorithm is just to find the partial derivative of the binary cross-entropy error function with respect to the parameters to determine the logistic regression model's coefficients for optimal values. So the task of logistic regression is trying to find the parameters beta naught and beta 1 from the original equation. We try to estimate those values by using the backpropagation algorithm. So let's see the forward propagation procedure in logistic regression by considering an example. If we wanted to predict if a person was obese or not given their weight, we would first compute a weighted sum of their weight and then input this into the sigmoid function. So predicting whether a person is obese or not is a simple binary classification problem. So the first thing that we can do is to multiply the weight of each person by the parameter theta plus adding a bias to get the output. So we need to calculate the weighted sum of the inputs. Next, we feed these x into the sigmoid function that we have seen before in order to calculate the probability of a person being obese. So the probability of obese of x is equals to 1 divided by 1 plus e to the power of minus x. Once we've used one of these methods to train our model, we are ready to make some predictions. Let's see an example of how the process of training a logistic regression model and using it to make predictions would go. First, we would collect a dataset of patients who have and who have not been diagnosed as obese along with their corresponding weights. So for this particular example, we can consider that the parameter theta is 1 over 12 and the bias is minus 7. So given the parameter 1 over 12 and a bias of minus 7, the equation for the linear regression will be 1 over 12 multiplied by weight minus 7. After this, we would train our model to fit our S-shaped line to the data and obtain the parameters of the model. After training using the maximum likelihood or gradient descent algorithm, we can estimate these parameters. These parameters are supposed to be estimated by using our model, but in this case, let's just consider that these values are given by our model after using the gradient descent algorithm, because here we're just trying to demonstrate the forward propagation procedure. Now we're ready to make some predictions. Imagine we got two patients. One is 120 kilograms and one is 60 kilograms. Let's see what happens when we plug these numbers into the model. So we already have the weight and the bias. Now, given the weight of the patient as 60, we can use the equation to get the output of -2. Simply by replacing 60 and putting it inside our linear regression algorithm. If we want to predict the probability of being obese, we have to use we have to use -2 in our next equation, which is the sigmoid function, and this will give us the probability of being obese. Notice that this value, once we fit it into the sigmoid function, is always going to be between 0 and 1. And another scenario is for patient 2, and his weight is given as 120 kilograms. And by substituting this value into the equation, we also get a value of 3. And finally, by substituting this inside of the sigmoid function, we get a value of 0.95. As we can see, the first patient, 60 kilogram, has a very low probability of being obese, and we have used a threshold value of 0.5. So since the first probability falls below the threshold value, then this person is not obese, and we classify it as 0, or it has a very low probability of being obese. However, the second one, which is a person with 120 kilograms, his probability of being obese is very high because it's 0.95, and it might be predicted as 1 or being obese. We can also show this by using a plot. So in the figure below, we can see the results given by the logistic regression model for the discussed examples. Here we can see that the 120 kilogram patient is placed here because the patient's weight is 120 kilograms, which is on the x-axis, and we have a value of 0.95 on the y-axis, which is the probability of being obese, and this is very close to being 1. And the second patient, who has a weight of 60 kilograms, has a probability of being obese is 0.119, and we can get this value from the y-axis and plot this point. So you can see that this patient falls below the threshold value of 0.5, so it's predicted as being not obese. So now, given the weight of any patient, we could calculate their probability of being obese and give our doctors a quick first round of information. That's all for the theory behind logistic regression, and in the next video we will see the implementation of the logistic regression algorithm using PyTorch. Thank you for watching this video, and if you like my contents, you can like, subscribe, and share this video.
Audio Jungle.